Let's take the derivative of the inverse cosecant function. First step we're going to want to do is take the cosecant of both sides. So if cosecant y equals cosecant of arccosecant of x. Now, the cosecant of arccosecant of x is just going to be equal to x because cosecant and arccosecant are inverse functions and they're just going to cancel each other out. So we have cosecant y equals x. Next step is going to be to take the derivative of both sides with respect to x. So we have derivative with respect to x of cosecant y. And notice here that we have a function in terms of y being with the derivative taken with respect to x, which means we're going to have to use chain rule, equals derivative with respect to x of x, which derivative of x with respect to x is just going to be equal to 1. So we have dy dx for chain rule times dy of cosecant of y and then we can go ahead and take that derivative. So dy dx times the derivative of cosecant y with respect to y is going to be negative cosecant y times cotangent y. It's all still going to be equal to 1. And if we go back up to the top, we see that y equals arccosecant x. So the derivative of y with respect to x is going to give us the derivative with respect to x of arccosecant x, which is what we're searching for. So go back down to our equation and see that we have derivative of y with respect to x right here. So we're going to want to solve for that. So divide both sides by negative cosecant y times cotangent y, and we're going to bring that negative up top, so we get negative 1 over cosecant, gotta fix that, cosecant y times cotangent y. So we have solved dy dx, but it's in terms of y. Generally, the inputs we have access to are going to be in terms of x. So let's go ahead and rewrite that. We can do that using trigonometric identity from earlier in our equation. Draw a nice little box here to do the rest of our work. So we can use this line over here, cosecant y equals x, to help us draw a right triangle, because the definition of cosecant y, the definition of cosecant is going to be hypotenuse over opposite side. So if we have an opposite side equal to x, or a hypotenuse equal to x, and an opposite side equal to 1, that'll meet those conditions. So we have cosecant of angle y, we have the hypotenuse of x, and we have opposite side equal to 1. But there's a problem. When you draw a reference triangle, whether you realize it or not, you're actually creating a system of vectors where you have the origin is right here, then this section here, the adjacent side, is the unit vector times your, so it's going to be I times the function that you're putting in, and it's going to be in the opposite side is going to be j times the function that you're putting in, and the hypotenuse is just going to be the sum of those two vectors. And I wrote it here, like I drew the triangle so that the vectors would be showing up in the in quadrant number 1, but they could be down here in quadrant number 4, they could be in quadrant number 2 over here, they could be in quadrant number 3 down here, they could be in quadrant number 2. So it's just by chance that they happen to be up here. But the hypotenuse doesn't have any direction associated with it. It is literally just the distance between these 2 points. So it's an absolute value. It cannot be negative. You can't have a negative distance. You can have a distance in a negative direction represented by these vectors, but you cannot have a negative distance. It's kind of in the realm of imaginary numbers and stuff like that. So the problem with using cosecant y directly to get the information is that here, since we have the absolute value of x, because by definition, by putting it into the hypotenuse, we're losing information, we actually only get a partial picture. This will lead to a final solution, which is only true for positive values of x. So what we need to do is rewrite this somehow. And so what we can do is use another trigonometric identity and say cosecant in general is equal to hypotenuse over opposite. Sine is equal to opposite over hypotenuse. So, therefore, if we take sine of y, not of this triangle, we're done with this triangle. If we take sine of y, we can just flip this upside down. We can flip this x upside down, because that's like saying x over 1. Just like I said over here, we have a hypotenuse of x over opposite side of 1. So sine of y is going to be equal to 1 over x. Now our goal is to get any values that are any functions that are in terms of x that aren't necessarily going to be positive. So when x is negative, the function should be negative. Our goal is to get anything that could be negative and has an x in it out of the hypotenuse and get it into one of these legs so that the information of direction isn't lost. So that means we have the correct sign if we go, for negative values of x. So what we can do here is say sine of y equals 1 over x, and sine of y equals opposite over hypotenuse. So why don't we say 1 over x is equal to the opposite side, and the hypotenuse is equal to 1, because 1 over x is equal to 1 over x over 1. So we can now rewrite that triangle using facts that we already know. And say we have a right triangle, sine of y equals 1 over x over 1. And so now we don't have the issue of losing information by putting it in the hypotenuse, which contains no direction. Now all we need to do is find this final side, the adjacent side. And to do that, we can say opposite squared plus adjacent squared equals hypotenuse squared. The opposite side, like we said, is going to be equal to 1 over x. So we have 1 over x squared plus adjacent squared that we're solving for equals hypotenuse is going to be equal to 1. So 1 squared. Now we're going to subtract 1 over x. So 1 over x in parentheses squared is the same as saying 1 over x squared. So we're going to subtract 1 over x squared from both sides. So adjacent squared equals 1 minus 1 over x squared. Take the square root of both sides. So we have adjacent equals square root of 1 minus 1 over x squared. And now you might be curious. It's a good time to talk about it because we were dealing with the hypotenuse question, like why is that an absolute value? Let's talk about why are we always taking the principal square root? Why is this not plus or minus? Why isn't adjacent equal to plus or minus the square root of 1 minus 1 over x squared? The reason is that we can't have a negative distance. You can move in the negative x direction a distance. You can move in the negative y direction a distance, but you cannot move a negative distance. So that's why we're taking the principal square root every time when we're dealing with these kind of geometries. So the adjacent side is equal to 1 minus 1 over x squared. Keep in mind, what we're solving for is cosecant y times cotangent y, and we want to put that in terms of x. So cosecant, from earlier we remembered that cosecant is equal to hypotenuse over opposite. And so in this case, hypotenuse is, so cosecant of 1, so cosecant of y is going to equal hypotenuse of 1 over square root, oops, made a mistake, cosecant of y equals 1 over x, which you're going to multiply by the reciprocal, make that division, it's just equal to x. Cotangent is equal to adjacent over opposite. So cotangent of y is going to equal, let's take a look at the adjacent side. Adjacent is square root of 1 minus 1 over x squared. So square root of 1 minus 1 over x squared. And then over the opposite side, which is going to be equal to 1 over x. So we have 1 over x. And that's going to be equal to x times the square root of 1 minus 1 over x squared. So going back to solve our equation here, we have dy dx equals negative 1 over cosecant of y, which is equal to x, times cotangent of y, which is equal to x times the square root of 1 minus 1 over x squared. So dy dx is going to equal negative 1 over x squared times the square root of 1 minus 1 over x squared. And we are done.